Yes, sir. We will start the session, sir.
Yeah, please.
Hello, sir. Sir, first I will give you a brief introduction.
Yeah, please.
Then I will hand over.
Yes, please.
Yes. Yes. So once again, very good morning to all the participants. Now we are moving on to the session 10 of Atal Academy sponsored 5 days national level online FDP on revolution and advances in e-vehicles. And this session 10 is about induction machine drivers. And this session will be delivered by Dr. B. Venkatesa Perumal, Professor, Department of Electrical Engineering, National Institute of Technology, Karnataka, Surathkal. I want to give just brief profile bio about Venkatesa sir. It gives me an immense pleasure to introduce Venkatesa Perumal sir. Sir has obtained his engineering in electrical and electronics engineering from Madras University and MTech in power electronics and drives from Bharati Dasan University in 2001 and PhD from Indian Institute of Technology, Delhi in August 2007. Sir has started at Vellore Institute of Technology, Vellore as a faculty from September 2001 to July 2003. Later, he worked as a manager R&D, BPL Healthcare Limited, Bangalore for a short period. Then he worked as senior design engineer at GE Healthcare, Bangalore from 2007 to 2010. Then as a senior design engineer at APC, India, Bangalore from 2010 to 2011, and as a senior design engineer at Sun Edison Energy India Private Limited, Bengaluru from 2011 to 2013. Then as technical lead at Sun Edison Energy India Private Limited, Bengaluru from 2013 to 2015. In the year 2017, he joined the Institute of Technology, Surathkal as associate professor in the Department of Electrical and Electronics. He is currently a professor and professor of NITK STEP. His area of power electronics applications in PV renewable energy, power electronics applications in power systems, or electric vehicle applications. Sir has 6 Indian patents and 1 US patent to his credit. He has handled various projects as principal investigator sponsored by DST and various other institutions. He has published 10 papers in international journals and many conferences into his credit. Sir has guided 20 UG students and 5 PG students and 6 PhD students. He is engaged in various extension talks as member in various committees across the country. He has delivered special lectures across the country and coordinated various programs and recognized with many awards for his achievements. We are very happy that we have such a wonderful person with us to deliver the talk in our Atal FDP. I welcome Venkatesa Perumal sir on behalf of our institution and on behalf of all the participants to this. So thank you, sir, for being here for us. So thank you very much for accepting our invitation and to be a part of this FDP, sir. Thank you very much, sir. Now the session will be yours, sir. Thank you.
Yeah. Thank you. Thank you for that brief introduction. So I'll start my screen sharing. Okay. So I hope my screen is visible.
Yes, sir. It's visible.
So yeah. So thank you for confirmation. So first, when I heard from the faculty who said that it's going to be conducted for Polytechnic, I was very much happy that all people are started looking at that next advancement in all the level in technical aspects. Okay, so in that way, I am very happy. Immediately, I accepted the invitation and I thought to deliver. And the topic, when they said that induction machine drive, so when I look at it, induction machine drive, immediately I got what we need to talk, what kind of audience are going to be there and kind of things. So there also I got a clarification. Okay, so all our faculty members for the FDP. So mostly are from the faculty side. So that's why I thought, okay, so before go into that, the technology aspects of what exactly we are doing it in very high-fi level, which we say that, okay, this is what it is going to happen. I thought I'll give a brief introduction about that induction motor itself, that machine itself. It's one of the very best machine till today. People cannot beat that induction machine motor, especially in motoring application. If you see that induction motor everywhere, people talk about the special machines, but if you look at it, the power rating and other aspects, you can't beat that induction machine. So that's why I thought, okay, I'll go with that very small aspects, and then taking into that the level where from that, okay, this is what we are learning, but that learning is where it is applied and what kind of a outcome we are getting. That's what I thought I'll present it over here. So my presentation flow is going to be like why induction motor and construction rotor part and equivalent circuit, then performance characteristics. Till this point, when they're looking at the title, yeah, it is very clear what it is, everything is there. But at the same time, the speed control, when it comes, all the above, if you are not clear with that, the induction machine is not going to be performed very well. So that's why I thought, okay, first we will give a brief about that, all the aspects. So why that induction machine, if you look at it, that today 85% of the industrial motors comes from that three-phase induction motor only. Even if you are talking about the power generation, wherever it is, the to make it the system to functional, some other subsystems will be there. Those subsystems are run by this exactly the induction machines. So we are talking about that towards the electrical vehicle point of view. I will correlate how that electric vehicle is related with this aspect of this induction machine. It is going to come in the subsequent slides. Okay, so just it is because it is very easy to control. If you look at it, that induction machine compared to the DC machine, you need a DC supply, separately excited, self-excited, different configurations, what kind of control you need to apply, different way you have to do this. But in case of induction machine, it is not that when just if you give a supply, it will start work and it will deliver that whatever the requirements. Okay, so that's what the main advantage of the induction machine. We don't look at it any other things. Here we talk about that stability problem. There is no stability issue, so it goes into that unstable operation kind of a things. Those kind of a things, it's not at all present in the induction machine. Excitation current, it creates on by giving the supply itself, and power factor is less. But today IE rating talks about IE4 rating. If you look at it, the standards, energy efficiency standard point of view, it's are coming above 80%, 85% of the efficiency. So IE5 rated things are, the motors are above 94% of the efficiency. But till IE4 point of view, people started using induction machine only. People say that the special machine is coming up. Yes, it is true, special machines are coming up, but it cannot replace that induction machine for the higher power level what we expect. Okay, so the power factor may be poor, but we can obtain the unity power factor in different way. That's what we are going to talk in at the end when we do the speed control on the machine. So just to give an overview, I know people might have come across with all the aspects of machine, everything, but still I thought, okay, putting into the basic picture of the induction machine motor. If you see that the front side, so it is coming from the washers and other things, bearing, and it is a rotor part, and the stator part, it goes to the bearing and the other side. So if you look at it, what kind of this arrangement, if you look at it, basically here, whatever the fins kind of a things. So why they, you see, this is not only the electrical aspects here, it talks about that mechanical aspects too. So if you are looking at these pins, what exactly it does. Okay, so most of them we come across the heat sink today. Heat sink is nothing but the resistivity offer for the temperature is very less, so that the temperature can be taken out. Basically, the temperature evacuation can happen in very easily. So that's where we talk about that heat sink. So in induction motor, you can see these kind of a fans which is used for evacuating the heat. Basically the losses whatever it is generated, it has been evacuated through this pins. Then again, if you see most of the induction machine, it is coupled with the fan arrangement, its own self-cooling. You see that the same thing, the system shaft is one side is connected with the load, the other side it is connected with the fan, and here the fan cover if they put, because it sucks the air this side and forcing inside, so that when the fan is rotating, it pushes the air here, it makes that system cooling is effect. Cooling is very easy. But if you look at it in your DC machine, the cooling aspect, if it is going very high loss and other things, and also the efficiency point of view, you cannot get it beyond 60% of the 60 to 65. But today, whatever available motors, we can get even 85 to 90% of the efficiency with the induction motor itself. It is for IE rated, IE 4 rated. Okay, IE 5 is the special machines which comes into the higher efficiencies. So basically, again, I thought, okay, so we can give that kind of a winding structure. I don't know, most of the time, today, if you ask me to go and check the winding, really, I can't do that. But still, we are trying to understand what kind of structures and everything. If you go to the local winding shop guy, he will never do anything. Just he will replace the coils, number of turns, and what is that, which is slot to which slot it should go. Everything he will easily he will make it, and he will make it the motor to run. He may not be an engineer. He may not be from the diploma guy. He comes with the experience. So that's where we have to give a respect for the experience. Today here I have put that slides to show up. Most of the people come across these kind of things, but we don't give a thought on it what exactly is happening. So concentric winding kind of a system, if it is there, so how the system is going to be, and distributed winding things are like this. So if you look at it here, the insulation sheets are used. Why insulation sheets are used? If you ask yourself, you will get more number of answers. Basically, this is one of the safety aspect for the coil insulation should not get damaged. For that purpose, they use this insulator, the paper, whatever they put that. Because basically, it is not a insulator for the magnetic field. It's a magnetic field is not going to affect with this plastic sheet. Okay, so that's why they use this particular one. And also, once the winding is done, you can see here again they insert one more plastic sheet over here. It should not get damaged from the other side also, and the winding should not come out. For that purpose, they have used these kind of a thing. And if you look at it, the winding is a distributed way. It goes into the slot and it goes. If you people are more interested today, what exactly people should know is, one is practical aspect, motor manufacturing. Before do that, only the area where we are not concentrating is magnetics. How the magnetic flux around the core, how it is going to be distributed, what is the path. So those things and all, you have to analyze it in a different packages. ANSYS package you can use, or ANSYS Maxwell you can use. Any of the magnetic packages if you are using, you can get the flux distribution, how it is. So this is only a point which I wanted to say for the people, those who are in teaching. Definitely they should use it and show it to the people how the magnetics is interlinked in this. Another aspect which I wanted to say here, the insulation on the coil, if you see that, it yields the cost of the system. It is going to, if I say that dielectric strength is 2 kilovolt, then the dielectric material what we need to use for coating on the wax coating or the coating material for the copper wire, it is going to be costlier. If I have presently, most of the pump manufacturer uses 900 volt insulation. So this is where people get the cost cut. So where we look at it, where the cost aspect involved, you have to do that. If you go to the one vendor, he will say that I will do it for 100 rupees. The other guy will say 1000 rupees. The material quality we are not looking at. So while taking any of the structure, first we should know what kind of a system we are going to develop and how much stress will come. What is the insulation level? That is also one of the important factors which we need to consider for the induction machine. And if you look at it, the induction machine, the two type of rotor, one is a wound rotor, another one is a slip ring induction, slip ring induction motor and cage motor. So here, the slip ring induction motor, again, what is that advantage if you ask that the torque, speed torque characteristics of the machine, during the starting time, the torque is going to be very high in case of a wound rotor machine. But in case of a solid rotor, cage motor, the starting torque is very less. Okay, compared to that, I'm talking about. Anyway, the starting torque, if it is not very high important, you no need to worry about the system. Okay, no need to worry about the system. Why I'm talking about that starting torque is it is very much relevant to the e-vehicle. So when you put that, see, the e-vehicle is nothing but it's a motion is required to move the vehicle from one point to another point. Rotatory motion is required. If I am using a hub motor, the induction motor itself, it's a kind of a hub motor. If I'm using, it is going to be a part of your wheel. But your entire car weight, if it is going to be a amount of, if I take it a 100 kg vehicle, if I take it a two-wheeler, Honda Dio or Honda, it is going to be 48 kg or 50 kg around approximately. I'm not saying that exact number. So this number, this weight is basically a dead weight. To overcome that, it has to produce more torque during the starting time. So the speed control comes into the picture. How we are addressing on those aspects, I'll put it into the V/F ratio control, which is there in the last, where we are discussing about that, how to improve upon. But at the same time, we can achieve that the torque requirement also with the solid rotor, basically caged rotor, by adjusting some of the factors in that. Okay, so basically it is going to be the rotor side and the stator side. So cage motor, the construction point of view, if you see that they have a slot over it, so that slot goes and the end ring is connected. But I don't know, reality, if you people open up and see that in the local manufacturer of motor, you will not get any copper. But for lower rating motor, it's not matter. But if you go for a higher rating motors, it is compulsory that the copper bars are sandwiched over there in the material and the end ring to connect it to get that. You know the skewing factor for here because of the locking, to avoid the locking on the machine. All those aspects will be there in the for solid rotor one. So just I thought, okay, I'll talk about that magnetic flux, how it is. You can see that at 0 instant, what is that maximum is there and what is the resultant flux which is available at the rotor. Okay, resultant flux, if you see that the flux created by the C phase, flux created by the C phase and flux created by the B phase, the resultant flux is available at this point. Okay, so here when the supply is applied, it is an alternating supply. Alternating supply creates the rotating magnetic field around the induction air gap. Okay, so I don't know, if you open up and see, you can't put back the motor as it is because the air gap is very, very tiny one. It's a very, very smaller one. Okay, so if you people are opening up the motor, be careful with all the aspects, and then if you are sure about it, you do that. Otherwise, you give it to the proper servicing guy. He knows how to remove it, how to put it, all the things. Otherwise, what will happen is it will make that damage in your coil, because exactly which I was talking about. You can see this, the air gap. If I talk about that, the air gap is in terms of 1 mm or 0.5 mm gap. If I'm talking about, okay, so under that condition, the 0.5 mm gap, if there is a misalignment, or if there is a sag in the rotor alignment, there is a possibility it will get damaged with the while rotating. Okay, so that's where we have to be very, very careful when we do certain things with the motor. Okay, so here the rotating magnetic field at 0 instant at omega t equal to 0, we are getting this kind of a flux. Next, if you see that at 60 degree, exactly the 60 degree point, because that the A has come up and then B is there, C is gone to 0, so your resultant flux is always constant. Here the magnetic field is rotating, but at the same time the flux is maintained as a constant, the magnitude value. So it is making that the rotatory magnetic field. So it is for 120 degree, and then it goes to that 180 degree. Keep on, if you rotate it, you can get that the rotating magnetic field on the system. So basically, how the synchronous speed, what we are getting it in 1/2 cycle, if you take it, this is a north pole, south poles changes to be happen in this system. So for 360 degrees, 1 revolution. So that 1 revolution or 1 by f seconds it will be taking for the time. Okay, so for 1 second, how many revolutions is there? F revolutions are going to be there. So it makes that, if it is a 60 seconds, 60 multiplied by both the sides. So it gives that me Guinness, basically in 1 minute, revolution per minute. If I talk about, it's a 60 F is a revolution per minute. But if you look at it in a 4-pole machine, 4-pole machine, it changes in the 2 times. So your number is going to be, it's basically the pole here is a 4-pole machine, means pair of poles is always considered for the system calculation of the synchronous speed. So looking at that, if it is at 60F, it is a 3000 RPM, and 60F, it is going to be 1500, and if it is a 6-pole machine, pair of poles are 6, if a pair of poles are 3, that is a 6-pole system, you will get this. So basically, pair of poles, if I am talking about here, that one makes that the 2 go up 120 F by P. This is for the synchronous speed on the machine, any machine, when we wanted to calculate it. The thing is, you can't make it the system frequency. If the frequency is 60 Hertz, you will get that the speed. But the rating on the machine, rated voltage and rated frequency, if you apply, if it is a 50 Hertz system, if we are talking about maximum, we are getting a speed is 3000 RPM. Some cases we want a very high speed, okay, very high speed. That is where the people goes for the special kind of machines where the torque requirement will be lesser, but the higher speed requirement will be there. So people uses that kind of a machine, special machines, most preferably because of the loss and efficiency aspects. But the speed requirement for industries are not going beyond the 3000 RPM. So people uses the induction motor itself for any of the application. So as we know that the equivalent circuit, most of us we come across with that equivalent circuit. Just to recap what it is, here if you look at it, that there's a stator resistance and stator inductance leakage component, you can see that. And at this point in most of my lecture, I used to say that you can see that here the resistance is marked over here. You can see that 3 peak is in the up and 3 peak is in the down. So this is the standard way of representing resistance. It is a IEEE symbol for the resistance. If somebody is asking, we have to draw like this. Similarly, for the inductor also, it is only 3 turns. So when you want to talk about that, the standard value of inductors, standard value of inductor. Once again, please. So standard value of a representation of an inductance, 3 turns should be there. It should not go beyond that. Similarly, for wherever we represent it, if you can check it with any of the packages. If you are using MATLAB, when you drag the resistance, it will come only this way. It will not be. Even PSIM, ORCAD, in any packages, they use the standard symbol. You can see that. So here you can see that the power is going to the rotor, how much power it is. This is the function where it is with respect to the slip, and also with respect to the rotor resistance referred to the primary side. Dash component is always referred to the primary side, and at the same time, the copper loss which happens in the rotor is this much. Total mechanical output delivered in terms of electrical parameter with the slip is a mechanical one. Okay, so the overall stator equivalent circuit, if we take it here, it is going to be equivalent circuit. That resistance, if I take it, we can rewrite it this function. So this is my mechanical output, exactly equivalent of mechanical output in terms of electrical circuit. So the conversion we used to do that mechanical to electrical, electrical to mechanical, pneumatic, so many other things are there. Same way, here it is a mechanical equivalent power in electrical. So that is my equivalent circuit where I am getting all the things. So the main thing is here it is a magnetizing component. Whenever you simulate it, you make sure that what is this value. Because when we take the simulation point of view, you are taking the motor value from the MATLAB or any other package. Make sure this value is very high, because this is always a loss component. It's a core loss component. It's representing the core loss component. This is for the magnetizing component. So the current here is one is the magnetizing current, another one is a torque producing current. So these two currents are going to be the main thing. This magnetizing current, you can't change it. You can't change the magnetizing current, because this is the one which makes that the power transfer from one side to another side. That the electrical power from one stator to rotor, and then rotor it is converting into that the electrical into the mechanical. Okay, so that is nothing but that the rotor component where it is coming. Without this component, we can't get the second component. So excitation current, if you look at it, if I do that, the most cases it will be 30 to 50% of the full load current, what it is going to be there in the motor rated current. So under no load condition, even if I take it 30% of the current, so then you think of this inductor is a dominant one, basically 30% of that. So the power factor of the system will be very, very poor. So basically it goes to that 0.65 or 0.7, it around that value it will go. So no load current is lagging exactly if you operate it. And I don't know, people have observed in laboratory about that the magnetizing current, how it will be for the magnetizing current over a voltage. So in oscilloscope you can't get it, because in this is one of the test aspect. I thought I'll tell right now in this case, you can put the voltage probe over here. Okay, you can put that voltage probe, it will give that voltage measurement in practical. And if you want to sense this current, if you put it, okay, and this current, you can take it into that value. So it goes like a spiky current, and then it goes not in the peak, it goes into this way. So you can see this no load current, how it is. Please kindly show these kind of a waveform to the student, so then he can understand really what exactly it is happening. It is not only creating my magnetic field when the core is there, the core, the magnetic flux is created. You can see that the flux is trying to saturate. It's not saturated completely, suddenly rising and it is coming. It's like a capacitor charging current in a DC. So your current will go if the current is a sinusoidal in nature, it is a worst power factor. You will get worst power factor. But this kind of a things, you will get the best power factor, but the distortion factor is more over here. But still, these kind of a waveforms, if they see that, it will give a reality. So when you put that current probe over here, you can do that. At the same time, if you do that, if you do the XY plot for that, you can see that the BH curve nature. I'm not saying that exactly it is going to be a BH curve. It's translated anyway. One is voltage, another one is current, magnetic field intensity, and flux density point of view. If you take it, definitely it will show your flux curve, how the flux is created and what is the path in the flux in which it goes. Okay. But in case of AC system, the flux should be cancelled, the positive side and negative side, the area will be equal. That also you can check it with by calculating the area in the positive side, area in the negative side. If you calculate it, definitely it will get cancelled each other. So otherwise, if the motor will get saturated, it will be, the saturation current will increase. So those things and all, if you do it even in the simulation, it gives that reality of that how the current profile is varies. So another thing aspect here, if I take it that the rotor losses, how we are replaced with that. So the ratios between that air gap power, what we are getting, and copper loss and the rotor loss and rotor output power. This is one of the relation where we get that. So 1 S and 1 minus S. It's basically the rotor loss component, how much it is going to be there, and rotor is how much is going to be there. And you can see that the relation, how it is. So active power flow, just I thought this will give an very brief of what is the power flow here. Just once again, if you see that the net torque, what it is created here, electromagnetic torque is created because of that electric power. So if I write it in terms of electromechanical torque one in terms of synchronous speed, and you will get the value. So it's basically the net torque is generated with respect to the synchronous speed is this much and mechanical speed is this much. So both the torques are equal. You can get it the net equivalent torque with this machine. Why I'm talking about the torque is more, I'll say that the torque which is comes from the load demand. So the torque is the one which can come from the load demand, the equal and opposite force created by the system, which is going to be the torque on this machine. Okay. So here with this, every losses are taken out, you are getting it. So in the case of a rotating machine in laboratory, normally people get the efficiency of 65%, and then it more or less around this number. But in real industrial machines are operated with the 85% to 90% of the efficiency. It is in the field. Okay, so just basically to show that the torque component, how it is dependent and what it is under no load condition, what all the current is impacting. You can see from these equations, basically these are all the again it is already all available, the book information. Just I want to concentrate on that torque speed characteristics. Just I'll go to that area. You can see here that torque is mainly electromagnetic torque is inversely proportional to the slip when it is running condition. Okay. If you see that I squared, whatever the calculation, if you do that I2 1, if you rotor current, if you do that, this 3 is indicating the 3-phase system. Sorry, just once again, I'll go to the yes torque. You can see that the torque, if it is less than S is less than 1, how it is coming, and S equal to 1, approximately equal to 1, it is going into that inversely proportional. So you can see that the torque speed characteristics of induction machine, if you draw it, you will get it. This is the one. Why I want to come up to this point is people talk about that in 2 to 3 decades back, the DC machines are the one which gives that exactly the torque profile very easy, and I can control the speed. If you talk about that the DC machine characteristics, this is the one separately excited machine I'm talking about. with respect to the torque when the load torque is increasing, but in ideal no load condition it will be there. This is basically the armature loss they will talk about. You can correlate my induction motor characteristics, which is very equivalent to the same as this one. Okay, so you can see that this basically here from here to here, it is the same, it is a replication of DC shunt motor characteristics. I can get it. Once I am talking about this profile also, but this profile is a unstable region. Motor will not work in this region at all. It will come out of a region, either it will go to the top side or completely it will shut down to the zero. So make sure that the why we are talking about that induction motor, the characteristics of an induction motor when I'm looking at, this is the induction motor starting torque and it goes. But at the same time, if I start about that, the current profile, it goes very high and then it goes into the same fashion and it goes to the zero. So now, if you look at it, the starting current is very, very high and torque is low because of that back EMF induced back EMF is not happening in the system. But here this is talks about that the rated frequency, the profile at which we are getting, this is the one at, this is the voltage, rated voltage and rated frequency. Okay, so before go to the next slide, I thought I'll tell that the induced EMF is always proportional to the frequency and flux is in the system. The flux is flux in the machine is created due to the induction, that basically the current flow through the stator coil, it creates the flux. Okay, so induced EMF, we can say this induced EMF this is nothing but V minus a stator resistance, stator component, the leakage component. If I put it, it will be there. Under rated condition, this will be very, very negligible component. We can say that V is proportional to 5. So this is my platform I'm setting. This profile, whatever I have drawn, it is for the V is proportional to F. Okay, V is proportional to 5 and F. Just you keep remembering that. Now, machine is without connecting load. If you are giving the supply and doing the speed control test, it is not at all considered as a test because it is under no load condition. It can behave as what we want, but under loaded condition, how it is behaving. So the standard load, if I take it's a constant torque load, that means this is the one. So wherever the intersection point I'm getting, there two intersection points. In this two intersection point, which is the stable one. So if you see that, if you give that slight increase in the speed, what it will happen? So it will come out. This is a divergence point. Basically, it is an unstable point. And if you give this one, it will bring back to the system here. So your operating point is stable, the only after the maximum torque region. Okay, so maximum torque from the machine, whatever you are creating, beyond this region only it is stable. If the NS is equivalent to NS, there is no induced EMF between these two coils because it's a relative velocity between the two. One, okay, when the two buses are moving, think of in an equal speed, inside the person who is sitting, they will see that it is a constant. It is nothing but a synchronous reference frame. So a reference frame theory and all, if you are read, you will be knowing that both the references are common. So when that way it will be equal. So here there is no induced one, and here. This is only for the constant type of load. In case if you have a load, torque is proportional to omega squared. It's nothing but a pump load. Most of our loads are relevant to that pump load. So operating point is coming here. You can say that your load torque is very high and it goes here. Here also, in this case also, your operating point will come at this point, which is where the stable operating point you will get. So if I see that the profile, yes, so profile, by seeing that the maximum torque equation, from the maximum torque equation, okay, so change in value, if you do that, the maximum torque occurring position you will get. So maximum torque occurring position will change with respect to the rotor resistor, basically the reflection resistance or equivalent resistance, which is comes from that. So the maximum torque occurring position will change with respect to the rotor resistance. Maximum torque is independent of rotor resistor, okay, independent of rotor resistor. So you can see that if we are adding anything, in case of a wound rotor machine, if you are adding any resistance, the supply frequency is constant and the resistance is changed, your maximum torque line is going to be constant, only occurring positions is changed based on this proportionate value. Similarly, if I take it the induction motor, V by F ratio, so here instead of the speed is constant, this is for 50 hertz, for example, you can take it, this is a for 50 hertz component, but if I want that lower side, my load requirement is this one at the speed of 25 hertz component, 25 hertz component. Then the load, if you want to create, this is the operating point. In this curve, if you look at it, that 50 hertz curve, it is nowhere it is coming to the speed at this point. So I need to maintain that V by F ratio is constant. Why we need to maintain constant? If I reduce that, the flux will be constant. V is proportional to frequency and phi. V by F is proportional to phi. So this case I'm getting it. So this case I'm getting it. The flux is proportional to that V by F ratio. If I apply rated voltage, rated frequency I need to apply. If I want this flux to be constant, this ratio need to be maintained as a constant. So if I reduce the frequency by half, this also need to be reduced by half, so that I can get the frequency. Basically the plot over here. But the maximum torque is independent of that value, independent of that the frequency is happening. So sorry, if you see that the maximum torque, it is independent of that, so my curve is shifted. Again, I'm coming back to that correlation. So you see that the maximum torque speed characteristics on the induction machine, by changing the DC machine terminal voltage, you can get that whatever the speed, and then the torque is increasing. This is the speed. Torque is increasing, the load will decrease. So if the voltage is rated voltage, you will get the same thing is replicated over here in an induction machine by making that V by F ratio, but you will not get the very high accurate speed control by doing V by F ratio, because the V is nothing but E, if you want to calculate V minus I stator current into the stator drop, whatever I have to do. If I do that, the stator leakage component drop, the impact will be there. But in the application, it is not very closer to the zero speed. The variation range is 1/3 of the rated speed to that the full speed, whatever we want to get it. You want to keep it. Sorry. So here you can see that the profiles are similar to that DC motor. What exactly what I wanted to convey, I am equating the DC motor characteristics with the AC motor by keeping that V by F ratio constant. In case if you are not making it this one as a constant, then what it will happen? See, you are applying a rated frequency, voltage alone if it is reduced, okay, voltage alone is reduced, then what it will happen is, it is not a problem. So you will do that. One thing is, the synchronous speed is not going to change. The maximum torque value will come down. Maximum torque value, because only voltage is reduced, your maximum torque is coming down, but you are not getting. Here, in this case, if I want to meet this kind of a load, only this supply, it will work with respect to the frequency, higher frequency and the higher voltage only it will be able to. Otherwise, it will be in unstable mode. So just you can see that the conversion, if I maintain this constant converter I need to use, and this is what I'm going to talk about elaborately, how we implemented these kind of a thing, and we have developed the practical system including the additional sources. This can be, if you say this motor is used for EV, yes, it is in EV. This motor, you want to use it for pump, you can use it any pump, pumping water. So the control structure is not going to change for any of these applications. What you wanted to know, how much speed it has to rotate. When you give a throttle force in the vehicle, it has to go more fast. The torque is not changing, only the speed is changing. The torque is the opposite force which is need to be created for the load, right? So it changes the speed, but the torque demand is same. Torque demand is same, only the speed need to be raised. So control parameter, if you look at it, the speed control, when you talk about, the torque value need to be maintained as the same value for all the speed. That is what the thing is important. So here, if you actually, this is not the correct picture for this frequency aspect. So if you change the frequency, you will get the aspects. So that's what we were talking about, the constant frequency. Now I got the constant torque, how much ever maximum I want to get it, I got that constant torque. But some of cases where I want to do that, the speed is more than the rated speed, then under that condition, you see V by F ratio is proportional to flux. But this V, once it is reached the rated value, we can't change it. So we can't change the rated voltage. So we have to apply the rated voltage. Only frequency will increase. So the denominator component is increasing. That's why the frequency increases means synchronous speed is changing. But the flux is weakening. So once it goes to the flux weakening mode, you are getting the shunt motor characteristics. So we can mimic the DC shunt motor characteristics with the induction motor. DC shunt motor characteristics with the induction motor. Kindly mute one participant, I think he has muted. So this basically replicating my field weakening mode DC shunt motor characteristics, exactly I can mimic on the induction motor. So I spoke about that induction motor, even in the constructional aspects, how we can do the control on it, what exactly. If now I know what parameter need to be controlled to achieve what. Okay, so if I want to change the speed and the torque is remaining constant, I need to change the V by F ratio below the rated speed. Above the rated speed, I need to change only the frequency, but my torque component is not going to be constant. Torque constant is not going to be constant. Here, exactly we have shown in the figure, you can see that the load torque profile, if the load torque profile is this one, when the speed is increased, the torque demand on the load is increased, but the torque is not the maximum torque. Okay, the torque is the maximum torque. So by setting that platform, what we have done in the induction machine, this is one of the example which I wanted to show. here, how we can achieve this? How we can achieve this? People talk about very hi-fi technology, field-oriented control, all other control. I don't want to do any other hi-fi control where I need a minimal control itself. So that's why this is one of the project where we have combined with the engineer and we have done this project. This is application is a pump application. Load can be any type of load. Okay. So when you take it from the grid, first thing of what you have to do is the power quality will come into the picture. When you talk about that, if I have an induction motor, just we studied about that induction motor, I said that when I connect it directly to the AC source or grid, directly to that AC source, what it will happen, it will draw the current and it can work only one speed, which is at the rated speed. Basically, the rated frequency is 50 Hertz and only one voltage. If I am applying line to line voltage is 400 volt or 450 volt, whatever it is, so it will operate at one speed. I don't have any control. First thing, I need to control this. We know V by F can do the control operation. At the same time, power quality is also important. Here the power factor if I talk about, it is very, very good. I need to draw only active component here and I need to supply the active and reactive power to the motor. What initial days people does? Just put a capacitor, calculate the no load power, reactive power, calculate the compensating capacitor. So you will get only the reactive power from here, reactive power from here, and it will start the motor to run. It will start the motor to run. But still, what we have not got in this case is the speed is not going to be controlled. Only applied load will make sure that where the operating point is coming. Okay, so exactly if I draw the speed torque characteristics of an induction machine, so it goes in this way. So here is my speed, here this is my torque. This region only a standard operating region. So you can see that this is only one operating point. No other operating point I will get because it is all are fixed. To vary the speed of the motor and the torque in entire range, if you want to get it, we can connect it the grid through the voltage source converter. Basically here it's a voltage source converter 1, converter 1 and converter 2 connected to the induction. So I'm putting my inverter. This is basically a inverter fed drive. So here I have a DC supply. Think of you have a DC supply and I'm done. Now problem arises. What problem arises? Induction motor will run because the inverter you can control it and you can get it. But the capacitor charging current, if you see that in the front end, it will be a spiky current. It makes my system to be troubled. What we have to do? So active component, instead of diode rectifier, instead of putting a diode rectifier, we have introduced the converter. This converter will convert the grid power into the DC. At the same time, power factor is unity. So it makes sure that always the power factor. And we have taught about it. This is one of the system where we are proposing here. Somewhere also some of the paper publication we have done it. EV, the motor will be running. This PV also can be top of the vehicle so that it can charge the power whenever excess power is there in the parking lot. Also it can charge. So that's what we thought when we have put one DC PV system over here to connect it to the DC side. So if I added the PV, previously the power flow has to happen from here to here. But at this case, what happened? If the power is injected from here, it can only inject, either it can go this side or this side. So this is becoming a bidirectional This is becoming unidirectional, and now this converter too need to be operated in bidirectional. So proposed configuration, if you see that the VSI1 is for the speed control of an induction motor, and VSI2 is nothing but the bidirectional power flow, operates in grid tie mode. So basically active power factor correction, or it is pushing the power to grid. So it has to do the two functions. The configuration helps to power fluctuation and robustness in solar. Actually, we have developed this one for water pumping system. This can be used anywhere. That is not a problem at all. The only thing is compressor type of load profile and pump type of load profile. If you match it, both are same only, because it is torque is proportional to omega squared. To optimize this thing, what we have done is the control. Here we have proposed that control for all the three stage. One is for the PV is MPPT, controller 1 for the speed control, and controller 2 is for that bidirectional power flow. So to talk about that MPPT power, first we should know that the MPPT characteristics. So if you look at it, this is what the panel characteristics. It starts from 0, the power it goes in this way, the current, short circuit current, and open circuit voltage. So if you have a solar panel, okay, if you have a solar panel and you are connecting with the DC capacitor, the switch, if you can put it, switch you can connect it at T is equal to 0 plus. What it will happen if the irradiance is maximum, if the panel is rated for a 8 ampere and 32 volt, initially when the T is closed, that switch is dead short kind of a thing, the profile will start at this point, and gradually pumping the current into the capacitor, the voltage is grows, and if it is reaches to this point, it will reach as that the maximum. So once that one is there, keep on it will go, and the current will start decreasing, and the voltage will keep on increasing. The voltage will go and stay there. Afterwards, the current will become 0. The no current will be drawn from that, because this is a PV is a current source, and it is pumping the power to capacitor. Once it is pumped, it is charged completely, the PV panel will open. So now if the PV is generating power, if it goes to the steady state, here I am not able to extract the power because the power balance is not achieved. This is the first condition which I am arguing. So if you look at it, the two-stage system, first boost converter followed by that MPPT, we can do that, and putting into that advanced panels, we can get it any of these things. VSI1 is the power flow converter between the grid and PV generation. So how we are controlling? So now I'm coming to that control aspect. You can see this VSI1 which is there in the figure. So I take only the DC voltage as a reference, and reference voltage, measured voltage. Compared through this PI and gain, I'm getting a frequency information. Once I know the frequency information, modulation value, if I know, I can make it V by F ratio is constant. So here what we did is only V by F ratio is constant way. We have applied the pulses to the speed VWM and we got the output. So that is being fed to the VSI2. But if you see that VSI2, it has to operate it in two mode. One is in a grid tie mode or active power drawing mode. How we can achieve? For this also, input is coming from that VDC only. Previous slide, if you look at it, VDC reference 1, here VDC reference 2. What is the difference between these two numbers if you look at it? These numbers are VDC reference 2 is going to be higher number than the VDC 1. Okay, VDC 1. So that the control will happen, the flow will happen in very easily. So it gives that D-axis component, basically the active component, and D-axis component, where whatever the component you want from the grid, you wanted to take it at 0 volt, 0 reactive power, then you can set it that IQ quadrature axis component into the 0. You will get that the reference current and you can generate it. So how it is converted from that ABC to theta, because basically I need a theta value here, right? That theta value comes from mains voltage, ABC voltage, phase voltage we have converted into alpha beta to theta. So it is basically from the reference voltage conversion, a 3-phase to 2-phase conversion, Clock's transformation and Park's transformation. If we apply, we are getting the same theta is used over here to make it that the current is exactly the reference current, whatever we are getting it, the original current what we are getting, and to compare with that the error current. So basically this current goes here also. This is my reference current, this is my measured current, this current will go to the block and we get the error current. That error current is generated for the PWM. So it acts as a or factor correction module or bidirectional power flow when it is required to push it the current power to grid. So this is the matrix which is used for converting into 3-phase into 2-phase quantity. Here I have considered all our balanced winding and balanced system. In case if you are taking an unbalanced system, the problem is what it will happen is zero sequence component will come into the picture, because in most cases the motor is not an unbalanced one, supply may be an unbalanced one, but here the motor control and primary control need to be taken care. If it is unbalanced, you need to address it. Here I am talking about balanced system. So at a given point of time, any time, if you instantaneous value of all sine omega t plus sine omega t minus 120 plus sine omega t minus 220, if you do that, instantaneous value, it will become 0, because it will negative side instantaneous addition. If you do that, it will be 0. So that's why we are not getting the zero sequence component, alpha beta component, DQ component, basically Park's transformation, clock transformation. If you do that, so you are getting the output. We have given that input basically for the solar 1000 irradiance up to 1.5 second, and after 1.5 seconds we have given 800 watts per meter squared. So basically the solar varies with the irradiance supply. So we are given it the give that variations. So it goes to the 200 for 2.5 seconds to 3.5 seconds, and then 3.5 seconds to 4.5 seconds, again 1000, and again it is goes to that 800 for that 4.5 to 5. Under that condition, you can see that the power drawn from the solar, you can see that it is going into that maximum power it tracks. At the same time, the DC voltage is maintained, because it is a DC voltage is maintained around 800 volt. In this case, we are getting it in the around 800 volt. At the same time, you can see that whenever the solar is generated, if the battery is not charging or battery or motor is not running, it can go to that grid current. So the grid current, here you will not be able to identify the phasor difference, whether it is in phase component or 180 degree out of phase component. That we will see in this other slide. Exactly next slide it is there. You can see that the speed of the machine is constant for throughout the period, and VAN it is like this, and IA corresponding current, you can see that. So it is 180 degree opposite. That means it is grid tie mode. The grid is, it is pushed to the grid. Okay. So at the same time, you can see here the solar is not operating. Here the solar is not operating. You are getting the waveform is in phase component. So the power factor is either unity for both the cases. Either power is sinking or power is sourcing. based on the availability of the source, based on the availability of the source. So the same thing we have developed in a hardware. What are all the things we have developed is a power board, control board, gate driver board, and each gate driver board will have a provision to that 2 driver of IGBTs and the system with the 6 gate drivers, because this system has to have required the 12 IGBT. So just I'll show that what is that power card. You can see this is the module which is there in the system. Basically, it is a Infineon is provided. They are the manufacturer of the device. We have a collaboration with them, so that we got the module. It's a 1200 volt DC bus you can apply, and you can do it in the 25 ampere system. See here, you can see this is one active inverter. This is another active inverter. Both are connected. I can connect the capacitor over here. So this gives me an power architecture directly. No need to change any other things. Connecting the different filters, ignoring them for necessary things. What kind of a current sensor we used is a LH 25P, whatever that is, a 25 ampere, and protective fuses and relays, more. All those things were the part of a system. Again, when you look at it in the control card, the control card consists of scaling, shifting circuits for sensed voltages and current. Because when you sense the voltage, you will get the signals. That signal, if you look at it, the signal need to be only 0 to 3.3 volt. If I am using any processor, the ADC voltage is limited between 0 to 3.3. So I need to limit my voltage there. So that's what we have done it. Some of the circuits where the output is coming. In case of 400 volt or 800 volt DC bus, you wanted to measure it for control purpose. The 800 volt is scaled to that around 3 volt. Okay, around 3 volt, because we have to work on the overrating of the system also. So overrating, if you wanted to work on under that condition, it is going to be a 3.3 volt. 3.3 volt is nothing but a overrated voltage of the bus voltage. It is around 1000 volt. We have kept it. What kind of a microcontroller we use? It is basically, it's an automotive processor. Automotive processor always costly, because the temperature withstanding condition and the moisture content in the atmosphere will affect the problem IC consumption. So all this, whatever the processor which we have used it is basically automotive rated, because it is going to be in automotive automotive system. So we need to take it on that. So other main thing component, if you see that what is the advantage of using that particular one is basically we have 12-bit ADC. So analog to digital conversion, when you talk about when you are taking the information inside the processor, analog component, if you are taking a 10-bit ADC, 2 to the power of 10 is the number where you can get it that the values. Okay, so a resolution bits, if you look at it, it's going to be a 10-bit or 12-bit. If it is a 12-bit, the accuracy level is going to be very, very high. So normally we prefer to have a 12-bit if the constraint is the basically money and other aspects. If it comes, we may be taking only the 10-bit resolution one. For initial prototyping and research work, we used to do with the higher resolution ADCs. So at the same time, these all the processors are having a PWM bandwidth with the deadband communication, all the communication CAN protocol, universal protocol, and transceiver, all those things it is having. The gate driver, if you look at it, the gate driver what we have used it a 1ED020, the Infineon one lead is, this is also provided by them, and 1200 volt isolation between the primary channel and the output and produces. So it is basically here, it is a 25 ampere device, 1200 volt. The drive current requirement is up to 2 ampere. So we decided using a 2 ampere. using a 28022. 44, that is the IC is for the flyback converter. So we developed the flyback converter. I'll show that the developed component what we have done it in that. So output gate driver IC, if you look at it, the peak current has to be supported. So most of the time we say that the gate driver is only the pulse is giving, but actually it should give that the voltage and current as per the specified one. So if that is the case, so we have to use it the higher rated current, because even though if it is a MOSFET, during the initial condition, it is not charges are not fed into the gate. So this requires a lot of current. So that's where the peak current requirement. You can see this system architecture. Here I'm talking about terminal 1 where we are giving a AC grid. Terminal 2 where the output power is taken to that any of the drive. So this is my inverter. This is another inverter. Here again it is a contribution which we will make it to that mention that the power supply for different gate drivers, input supply, also power conditioning circuit supplies are made out of it. Just I wanted to show this. You can see that the module here, but whatever the module which I was talking about, that we have used it over here. So this is the module back. Actually, it is there in the back side. So this is the DC bus capacitor. Here you can see this LM current sensor. Basically, this is for the AC current sensing. This is for the DC current sensing, because the balancing was because when we use that two capacitors here, the capacitor balancing, voltage balancing is a bit difficult. So what we did is we have put that the resistance across this one. It solves the problem 10K and 10K. We have put that problem is solved, but at the same time we need to sense that in case of ESR, the value of ESR, if it is making the difference, you have to make sure that whatever the component, the ESR value also into the picture. So to avoid that, we have put that additional two current sensors and sense that. This is, you can see the fuses are there, and relay, fuse and relay, and this is the current one. This is a typical application, pump load application, solar. We can see that when we do this, what it is exactly, it is a conveyor belt. So EV, what we are talking about, don't think only the two-wheeler and three-wheeler. In industry, even if it is going into the coal bed, coal plant, coal is transferred from one place to another place through the conveyor belt. The conveyor belt also need to be attached with the motor. That motor need to be validated for this kind of application. So normally to do the cost cutting, people have done it. The 100 places, if I have a motor, if I have a 100 places motor. So what we used to do is same controller can be used, but the length of the cable will increase. Yeah, length of the cable is increasing and you are giving all these things. The problem is in case any one motor is failed, immediately the system will have a problem. So that system, how we are trying to do that compensation. So by putting that cable, so you see that if I have a 100-meter cable between that, the inverter which we are supplying power to the motor, VSI1, basically VSI1, if you are supplying it, then what all the effect will come. So basically here it will be a cable reflection. What is that meaning? The voltage is here at this point, you can see that. So basically it is a square wave. So rate at which changing is very high, and also this system is not going to allow you to do that kind of a thing. So here what exactly is happening is reflection voltage. If I take it my waveform, this is my waveform, this is what expected waveform, but if because of this long cable, the voltage will shoot to the higher value and it is to be lower value. So because of this overshoot, the insulation which I was talking about, 900 watt, So if you take it the 900 volt insulation, because the cost cut, people uses the 900 volt mm, insulation. So under that condition, the possibility of induction motor failure will be there. So to address that, we have done some of the work. I'll show that the results also there. You can see that in the waveform which is we created and we have done it, and we have captured at the 33 hertz what is the value. Similarly, we can see that for the 50 hertz what is the value. So here in the 50 hertz, the size of the waveform, you can see that there also you can see that. Okay. So your timing is more or less double, so your frequency is decreased. At the same time, the voltage is also voltage waveform if I take it. So you can see that the reality. So we have done that. We have done a gate drivers 1, 2, 3, 4. Again, this is my control card. This is my power card. Okay, this is my power card. You can see that the voltages which is coming in the oscilloscope. Basically, it's not showing this any of the spikes because we have not connected any of the wire into that. Okay, no wires and other things are not connected. So we were talking about that the stator current and stator voltage. So this is the one is the voltage. The pink is the one is the voltage, because you can see that the fundamental component alone. If I take it only the fundamental component, we are getting that. And if I put that LC filter, that LC filter will take care of that the reflection voltage. So what we have done it, we have introduced the inductor over there. So LC filter, we have used LC filter, we have used it, and then it is given to the motor. Then it is given to the motor, induction motor. But the thing is, because of this large value of inductance, our power quality is getting problem. To avoid that, again, if you look at it, they have done it, the calculation for this, and the heat loss is more. So the same configuration we ran for 10 minutes, not even 10 minutes. The value of temperature gone up to 1. And similarly, when we look at it, that with a coil and core, if I do that, the temperature is within that limit. So this is the one is preferred one. You can see here the temperature variation, how much it is there in a proposed system. You can see that very clearly, the temperature is not gone. But here you can see that the temperature numbers are going very high. Okay, so numbers are going very high. So this makes my system before starting and after starting at some instant within 5 minutes or 5-10 minutes, immediately the things are getting changed. So within 48 minutes, the voltage is the coil loss is increased like anything. So what I have done up to this point is just I talked about that induction motor and all related with that induction motor, and how it is being working and what kind of a control we can apply. Even you can apply that field oriented control, but when you want to start with some work, you start with V/F ratio. So that's where we wanted to talk about this hardware more. You can see that all the gate driver cards, whatever we are inserting here. So we have not used the other side, only one side of the board we have checked it. So that's where you can see 1, 2, 3, 4. The other two are not inserted over here. So this is my control card is 1,000 component, 1,000, not more than 1,000 components were there in that particular one. So it makes sure my signal conditioning and then ADC part of the system. So this is again actually inductor voltage. If you zoom it, you will get it, and the other one is this. And we can see here what all the component we have used it for developing this kind of a system. Where exactly it is used, if you look at it, any of the application, wherever you wanted to design, you can use it. Okay, so floor is open for the, I don't want to take it because they have given 2 hours of thing. But if I talk about, I can talk about one more topic also, but I don't want to do that. Why? Because Why? Because why? Because the thing is, people will get 2 hours of continuous lecture is not going to make any sense. People can interact with me practically. If you have any queries on the system which I talked about related with the EV, if you have anything, I can give answers. Floor is open for you guys.
Dear participants, kindly if you have any questions or any queries regarding the session or regarding electric vehicles, kindly unmute yourself and ask to the resource person. Thank you.
You can ask me anything related with the EV, how to charge, charger part, or even in the hub motors, switched reluctance motors, anybody is working or on those aspects even.
Sir, I have one doubt.
Yeah.
That is how the speed of the electric vehicle give impact on the battery life, sir. Any idea that?
Battery life you are asking. Yes,
Yes.
exactly what it is. Basically, you see that in normal case, UPS you take it, UPS in home UPS if you are taking it, suddenly if you put a load onto the battery, what it is happening, it is trying to go to the under voltage, it will cut off. If you, the load point is 100%, if you are trying to do it for 125, momentarily it will go to the trip mode, because it is trying to draw that more thing, and internal resistance will come into the picture and it will damage the cells. Same way, if you are giving that the speed from reference from one point to another point immediately without slowly rising, it will impact the battery life. How it is? Because internally trying to discharge more current, and that cells are getting damaged. Okay, so if you are talking about nickel cadmium battery or any of the lead acid battery, it is not suited for any of the electric application. Okay, people uses that still, but that is not advisable. Okay, but shield maintenance batteries are using, it is okay, but at the same time, if you look at it, most of the cases EV, it comes with the lead, nickel cadmium or other batteries. So those batteries, what it happens is impact is going to be more, and you are trying to take it out. If you calculate the lifetime calculation with the battery manufacturer data sheet, it will reduce your life. Okay, so the calculation can be taken from the battery data sheet. How much life it will go when I try to discharge it is very fast.
Yes, sir, I have another one. What are the things we can do to increase the life of a motor or battery?
Motor,
Because
if you are talking about see, exactly I'm coming to that application oriented, because I have seen all these battery used in UPS application as well as the electric drives application. If you in any other application also, if you have a battery at any places, if you are charging it for 100%, you don't discharge it to 80%, again charge it 100%, 80%. That will also lead you a battery deterioration. So if once in a month you completely discharge it, it should go to the under voltage and then you charge it. So to charge it to the 100%. So that will make sure that the life of the battery is completely for the throughout that life, which is specified by the manufacturer. 5 years if they are giving warranty, definitely it will work for the 5 years. But if you are trying to do it 100%, goes to 80%, 100%, that is also not a good for the battery life. If you want to improve the life, once in a 15 days, you have to completely discharge and charge it. This you can try it out with your even your mobile phone. You see that people are in a 70%, again they will charge it. They don't allow it to go to that low voltage at all. But you do it that one periodically for over a period. Okay, 15 days once, completely go to the low battery and then charge it. Then the life will improve. This is for the battery life. But in case of machine, motor life improvement, it is basically how much stress you are applying onto the machine. Actually, all the vehicle rated motors are having the capability to withstand that higher amount of current. Okay, so that is not a problem. But only thing is the insulation level, what it is there, it is getting affected with the, because of the control application. There you need to make sure that with the, see, if you are a designer, definitely you will prefer to do the cost cutting. That cost cutting will impact the life. For running of the machine, it is not a problem. As a user, you can't do anything, but as a designer, if you are asking me, we have to take care of that insulation level on the battery, insulation level on the winding, and how much stress across that voltage stress across the winding is applied. That need to be taken care.
Yes, thank you, sir. I am very much concerned that because of this, all electric vehicles are completely managed by battery.
Yeah.
So and the motor. So in the places like coastal areas, when we get heavy rain and heavy flood.
Yeah.
So if once if the water gets into the inside the car or any lower places, then will it possible to get back things? Or
no
not?
problem. No. Actually, this particular one is a vehicle standard is taking care. Your all systems are IP65 or IP67. Okay, so that means water should not enter at any cost of any point of time. I will dip it inside the water also. Nothing will happen to the control system. Okay, still it will work. That is what the advantage for electrical machine, electrical vehicle basically. Whatever the flood case or any other cases, definitely the motor will work because of that. It is IP67 rating. Okay, so the controller will not fail. Battery is also in the enclosed manner. It will be used.
Yes, sir. Thank you, sir. Thank you. Any participants have any questions? Kindly unmute yourself and ask the questions. Thank you.
So if you are not having anything at present, also don't worry about it. You can write to me. I am the person wants the everyone should get the technology. I don't want only it is to be with the level of the people it should be. I want to disseminate what I know, because talking in the PPT, putting the content, it is very easy for everyone. But when it comes to the reality, I showed that the last 4 slides when we have taken the waveform, when we ran the machine, what exactly it is happening, it will come by an experience. So if you need anything, you can write to me, bvperamal@nitk.edu.in. I'm happy to support all. Thank you.
Yes, sir. Thank you very much, sir. If no participants have any questions or queries, I will wind up this session. So I thank Venkatesa Perumal sir for accepting our invitation and delivered a talk on induction motors. And I am very happy that sir accepted our invitation. When I just messaged them, they were very happily accepted our invitation. And today they are presented very wonderful session regarding induction motors. Hope everybody enjoyed this session and gained some beautiful knowledge in this regard. So I once again thank Venkatesa sir on behalf of our institution and on behalf of all our participants for delivering a beautiful lecture to us. Thank you very much, Venkatesa Perumal sir. In the future also, if we get any Atal FDPs or any other FDPs we are conducting, definitely we will come back to you.
Not only for your FDPs, I am ready to support even the regular lecture somewhere. If you are feeling that I can talk on some topic, I am open for it. Okay.
Yes, sir. Thank you, sir. Thank you for your support, sir. Definitely, we will come back to you in the future, sir. Thank you, sir. Thank you so much.
Thank you. Thank you, one and all. Thanks. Bye.
Yes, thank you, sir. So, instructions to participants. So next session will be started from 1:45 or 2:30 p.m. So that will be on NEP 2020, the role of technical education. And for that session, you already know that the eminent personalities from Government of India, scientific advisor is also joining to the session. And also a professor from IISc is also joining to the session. Don't miss out the session. Kindly join before 2:30 p.m. So because we have shared the links to all our colleagues in our Karnataka Government Polytechnic Lecturers group also. So maybe there will be a lot of persons who are going to join the session. So kindly, I request to join as early as possible. Thank you. Thank you so much. We are closing the session. Thank you.